Hello everyone, my name is Arash. I'm a PhD candidate at Aalto University, and today I'll be talking about reachability. More specifically, I'll be talking about reachability in the context of timestamp data, such as temporal networks. So the problem of reachability is basically starting from a node A, is it possible to reach a node B if you are only allowed to move through the links of the network? On temporal networks, this would translate to something like this. Starting from a node A at the time t0, is it possible to reach a node B before sometime t1? The problem is more or less equivalent to the study of spreading processes. So another way of putting this is to say, how far can something spread over the network? For example, you can think of information spreading over the communication network or disease spreading over a face-to-face interaction network. Now, in a static network, you can easily calculate the set of all reachable nodes from a single node using breadth-first search algorithm. On a sparse network, that would correspond to a time complexity of OV, where V is the number of nodes in the network. On a temporal network, you can simulate the spreading process from your source and go through all the events in the order of timestamps, and that would translate to a time complexity of OE, where E is the number of events. If you need to calculate reachability from every possible starting point, however, that is, from every node for the case of static network, and from every combination of node and starting time for the case of temporal network, this would translate to OV2 and OE2 respectively. The problem I'll be discussing here comes down to this. How can we calculate reachability from every seed in better time than OE2? Now, before we get there, let's go back one step and think about what is it we're after. Usually, we're not that interested in the actual set of reachable nodes, but one of these three. First, how many unique nodes are accessible from each possible initial condition? Second, how many events can participate in the spreading process? And third, how long can a spreading process last until it dies out? If we translate these three into the disease analogy, the first one would translate into the number of people that can be exposed. The second one would translate into how many face-to-face interactions can cause the spread of the disease. And the last one would be the lifetime of the epidemic. You're most probably already familiar with temporal networks, but let's go through it very quickly. Temporal networks are a set of events, E1, E2, etc. here, where each event involves two entities, called nodes, and a timestamp. There are all sorts of variations on this. For example, where there can be more than two nodes involved in each event, that would be similar to hypergraphs, or where events each have an intrinsic directionality. For example, in case of people sending each other messages, where information can only go from the sender of the message to the receiver of the message. Sometimes events can also have a latency, which is when an event is not instantaneous. For example, a letter might take some time to arrive at the destination. So in this figure, you can see one example of a very simple temporal network. Here, V1, V2, V3, and V4 are the entities or nodes, and each arrow is an event. The horizontal axis shows the progression of time. Now here is one example path on the same network. As you can see, it is only traversing the network through events. Now let's take some baseline measurements on how long it takes to calculate reachability from every initial condition. Now, our largest dataset is the mobile dataset, which is more than 300 million events. This is a dataset of all the mobile phone calls for one of the carriers in a relatively large European country from 2008-2009. Here, each event is a mobile phone call between two phone numbers, and there are a few million unique phone numbers involved. What we've discussed up to this point is shown in the delta t equals infinity column. Now, for the mobile dataset, we've estimated that you would need more than a millennium of computation time to calculate reachability from every single starting point. Now, of course, you can always sample from the initial conditions, but that would translate into estimation error. And in some cases, for example, if you're interested in the tail of the distributions of one of those quantities we've talked about, excessive sampling might actually cause issues. So how did we change that? First, we need to define some stuff. Let's say event E1 is adjacent to event E2 if they share at least one node and E1 takes place before E2. Of course, you can very easily extrapolate this definition for other types of temporal networks. Another way of putting it is this. If Alice hears some quality gossip during a phone call from Bob at time T2, can this fact be possibly attributed to Bob's call with Carol at time T1? Well, it can if T1 is less than T2. but it can never be attributed directly to a call where neither Alice nor Bob participated. Now, just to make this crystal clear, we're not actually talking about an event being caused by another event. We're talking about the causality of an effect spreading between these events. Now, let's form a higher order graph based on this adjacency relationship. This will translate a temporal network into a directed graph, where every node is an event and the adjacent events have a directed connection between them. We can also preserve time difference between events in form of weights. The event graph is also acyclic, since causal loops are impossible. Adjacency relationships always follow the direction of time. Now here is the same temporal network as we saw a little bit ago, this time with the event graph representation. In this example, events E1 and E2 are not adjacent. There are no links between them in the event graph below, because they don't have any entities in common, even though E2 happens after E1. Well, on the other hand, E5 and E6 are adjacent, because they share the node V3, and E6 happens after E5. So there is a link from E5 to E6 in the event graph. Let's now think about a list of events, where each two consecutive events in the list are adjacent to each other. On one hand, this would be a valid causal chain, which is another way of saying that this would constitute a valid time-respecting path on the temporal network. On the other hand, this would constitute a directed path on the static event graph. We know that the spreading process can only spread to temporal network over time-respecting paths. Now we can see the equivalency between paths in temporal network and paths in the event graph. Now, here's an example of a valid time-respecting path from some initial condition and the same path over the event graph. And here's another valid time-respecting path from the same initial condition and its equivalent path over the event graph. We can also narrow down reachability by putting more constraints over the definition of adjacency. A common example is where you don't consider events that happen temporally too far apart from each other as adjacent. For example, if you're studying spreading of a disease that has a limited infectious period, that would determine a temporal upper bound on the adjacency between events. We will be calling this case the limited waiting time reachability. Clearly, you can define a normal or unlimited reachability as just a special case of the limited waiting time reachability, where delta t equals infinity. Now, applying limited waiting time and event graph is as simple as pruning links with weights larger than our specific threshold. In this example, all adjacency relationships with the time difference larger than 3 units of time are removed. Note that now there are no valid paths from E1 or E3 to other events in the network, meaning that if, for example, one of these events is the first instance of a disease spreading, it would definitely die out after E3, and it is impossible for that disease to spread to nodes that are not involved with E1 or E3. Now that we have a directed network representation, we can see that the out component of an event represents all the events where there is a valid path from one of the nodes from the time of that event. Similarly, in component would be the set of all nodes that you can start from to reach a specified event. As the event graph is a directed acyclic graph, there are no externally connected components with a cardinality larger than 1. Now going back to the three quantities we talked about earlier, the number of events that can participate in a spreading process would simply be the cardinality, or the number of unique members of the set of events in the out component. The number of unique nodes that can ever get exposed is the number of unique nodes among all the events in the out component. And finally, the lifetime of the process is the maximum time of all the events in the out component set, minus the time of the initial event. Another way of thinking about these in and out components is to borrow the light cone analogy from relativity. Let's think about an event as a point in spacetime. The set of all other events that can possibly be causally affected by this event would be analogous to the future light cone of that point in spacetime. If one event is not in the future light cone or out component of another event, you can absolutely rule out any causal relationship between the two. You can also apply this analogy to the in components and the past light cone. Calculating out components of all nodes at the same time is algorithmically easy. The trick is to go backwards in time from the last event to the first one and accumulate events as you go based on the adjacency relations you see at each step. This is still quite costly, both in terms of time complexity due to the repeated application of the union operator, and the space complexity for storing all those sets, where each one can grow as large as the number of events in the network. Now, of course, there is a way to get rid of this ON cost for both union operator and the space complexity for storing the sets. As long as we are only interested in the number of unique elements in those sets and not which events are in it or not, we can replace sets with a probabilistic cardinality estimator data structure, such as HyperLogLog. This way, you can expect constant merge time complexity and constant space complexity for storing the sets. But this would also add a relative error to each estimation. But you can reduce the error to any arbitrary percentage you like by just using a larger container for each set. For example, a 640 byte HyperLogLog container can estimate cardinality of a set with a plus or minus 3.2% relative error. So what is the end result? We can calculate all these three quantities from every possible starting node and every possible starting time on a temporal network with OE log E as opposed to OE2. In exchange for that, you would get estimations with non-arbitrarily small errors instead of exact results. Let's look at some benchmarks now. If you remember the 1.5 millennia mobile dataset from before, that is the first row on the table you see, with this new algorithm on the very same hardware, you would be able to get estimates for the same quantities, plus or minus 3%, in something like 100 minutes. Now that was all. Thank you everyone. The slides are available on SpeakerDeck and the implementation is there on GitHub. The paper is open access on PRE, but the same thing is also available on archive if that's what you prefer. Thank you.